Okay, we're on lesson 6D, part 3. So this is the last lesson of the unit before the unit review and test. This was the homework. So the power of a test is the probability, and this lesson is mostly conceptual, not a whole lot of figuring, calculator use. It's about the power mostly. So the power of a test is the probability the test will find convincing evidence for the alternative when a specific alternative value parameter is true. It's important to write down that definition because that's how we kind of interpret the power. We use that wording sometimes. It's related to the probability of a type 2 error for the alternative. In fact, it's I would think of it as like the complement of a type 2 error. So type 2 error, if you remember, we talked about that's beta. So 1 minus beta is the power. If you move that formula around, you can solve it for another one there. But here's what I mean. So if you bring back up that chart that we had, so beta is the probability of a type 2 error. And so the power, which is when you reject the null, and you did that correctly because the alternate is actually true, the null was false. So when you make that correct decision, what's the chance of that happening? It's 1 minus beta. So if there's a 3% chance of a type 2 error, there's a 97% chance that you correctly reject the null when the null is false and the alternate is true. So it's directly related, it's inversely related, I should say. So if beta is 7%, if it's a 7% chance of a type 2 error, then there's a 93% chance of correctly rejecting the null when the alternate is true, which is called the power of the test. So it's a term we use there called the power. So again, power is when the null is actually false and the alternate is true and you reject it, right? So a significance test based on a random sample of size n, significance level alpha, will have greater power and smaller probability of type 2. So let's think about that. So if we want greater power, we have to reduce the chance of a type 2 error. Does it make sense? If we want greater power, we want a greater power for our test, we have to reduce the probability of type 2 because they are conversely or inversely related there. Okay, so what are different ways we could do that? Well, this is a great way to do it. If you can afford it, the sample size is larger. So if you choose a larger sample size, that reduces the chance of, I believe, both types of errors, type 1 and type 2. It's always better. So if type 2 error goes down, so type 2 went from 5% to 3%, power went from 95% to 97%, right? So it's inversely related. So if type 2 error goes down, power goes up. So that's one way. It's a good way. Significance level alpha is larger. So let's think about that. So here's the thing about, so alpha is, so they're saying increase the chance of a type 1 error. Type 1 is alpha, right? So if you went from your typical 5% to a 10% alpha level, that means you're going to have more type 1 errors, which, by the way, type 1 and type 2, they're not exactly linked in the same way that, power and type 2 are related, like 1 minus that, the exact converse of that, but they are related. In other words, if you have more type 1 errors, you're going to have less type 2 errors, and vice versa, typically. So if you increase alpha, beta is going to go down, which makes power goes up. It's all kind of related like that. The null and the alternate parameter values are farther apart. So that's kind of interesting. So if you get results that are really unusual, so not just like, we expected this percent, we got really unusual results. The further apart the null and, the sample that you took, so to speak, if they're far apart, that gives you more power. So when you're comparing two tests that are similar in every way except the sample you took and the null are further apart, that one's going to have more power. And then the standard error. So I guess I didn't really think about this, but I guess having samples that are further apart reduces the chance of a type 2 error. The results are more obvious that way usually. You make less errors, I think, when you have obvious differences there. The standard error of the statistic is smaller. So standard error is standard deviation. So if you have a smaller standard deviation, that means you have less variation, which I guess means the errors, type 2 errors, go down because power gets more. So a larger sample size increases power, also a smaller standard deviation. So it's not, I don't know, we can create that, but that's, oftentimes those are kind of related, right? If n is larger, typically the standard deviation is going to be smaller. So that's very much related to the size because standard deviation is part of the formula for standard error or standard deviation, essentially. So going back to potato chip situation here, it says in one shipment, 11% of the potatoes have blemishes. Remember, 8% was our kind of level where nothing's going on here. It's the null. In this case, the power of the test is 76.4%. So they just told us the power, right? 76.4%. Can we interpret the value? So go back to your definition. See that at the top? The power. What is the power of test? It's the probability the test will find convincing evidence for the alternate, and correctly do that, by the way, right? Because the null really is true. The alternate, the null really is false. The alternate is true when a specified alternative value of the parameter is true. So this is the chance, the probability that the test will find convincing evidence for the alternate when a specific, so given a certain sample, in other words. So let's try this. So 76.4% is the chance or probability of finding convincing evidence that the percentage of is less than 8% there, greater than 8%, right? I think that confused me. The alternate should be greater than 8% there. They said it correctly in the blue there, but not in the above. Confused me. Sorry. If 11% of the potatoes in the shipment, in other words, if we take a stat of 11%, evidently there's a 76.4% chance that the producer will find convincing evidence for the alternate, which is that the percentage is greater than 8%. But it's bothered me that needs to be fixed. Let me fix this. Okay, I fixed that. Now it's going the right way. Okay. How will the power change if the producer uses an alpha level of 1% instead of 5%? So the alpha level goes down. So when alpha decreases, type 1 error decreases, type 2 is going to increase. If type 2 increases, type 2 goes from, I don't know, 3 to 7% or something, then power will decrease. So alpha and power actually go in the same direction. So if alpha is increasing, power increases. If alpha decreases, power decreases. So how will power change if alpha increases? So if alpha increases, power has to increase. Power will decrease. Okay, I read that statement wrong. So it says, how will the power change if the producer uses alpha is 1% instead of alpha equals 5%? So that's saying it started at 5%, it went down to 1%. So the power goes in the same direction as alpha. So if alpha is decreasing, power will in fact decrease. Sorry, I just didn't, I thought it went from 1% to 5%. It actually went from 5% to 1% when you read that carefully. So decreasing the alpha level from 5% to 1% makes it harder to reject the null when the null is true. And how will the power change if the producer uses 1,000 and it's a sample size that's much larger? So if the sample size goes up, the chance of an error goes down, generally, I think both of them. And so power will increase, right? Because it's an inverse relationship. Power will increase, gives more information about the population proportion P is what they said. How will the power, so assuming the producer selects a random sample of 500, uses alpha as 5%, how will the power compare to the shipment with 11%? Okay, so in this one, 10% have blemishes. Well, that's not as extreme a result. Remember, 8% is our null. 10% is closer to the null. So power will decrease, right? Because it's a smaller difference. We want, for more power, we want a larger sample, like the sample and the null need to be further apart. That would be, give you more powerful results. The power would be greater. Wow, that's tough on the brain, isn't it? So see if there's a couple examples here we can do. Okay, let's just do this example. So the Center for Disease Control and Prevention claims that 9.8% of U.S. children ages 4 through 17 have ADHD. Company claims it has developed a new vitamin tablet that will lower a child's risk for ADHD. Researchers will administer the vitamin tablet to 200 volunteer children younger than age 4. Wow, so they're diagnosed really early. Subjects will be tracked throughout childhood, and the researchers will record the proportion of subjects, they haven't developed yet, who do eventually develop ADHD. The researchers will perform the test at the alpha equals 5% alpha level, and the null is P is 0.098. The alternate, we think, is less than that. So where P is the true proportion of children, like the ones in the study, who would develop ADHD given the new vitamin tablet. Okay, so part A. Researchers believe that the vitamin tablet will reduce the incidence of ADHD to 4%. Assuming this is true, the power of the test is 67.9%. So what that would mean, so if the true proportion of children in the study who are going to develop ADHD is 4%, there's a 67.9% probability that the company will find convincing evidence for the alternate, something like that. So, and I should say for the alternate, which is it's less than 0.098. So that's the official solution right there. Part B, how will the power change if the producer uses an alpha level of 10% instead of 5%? So if alpha is 10, so alpha increased, beta is going to decrease. If beta decreases, 1 minus beta, which is power, is going to increase. So alpha and power go in the same direction. So if alpha increased, then power should increase. Increasing the alpha level, it makes it easier to reject the null when the null is true. Yeah, it's easier to reject when the alpha level's increased. So part C, how will the power change if the producer uses n equals 50 instead of n equals 200? That's not good for power, right? We want a larger sample size, which reduces errors and helps power to increase. So that's going to make the power decrease. It gives less information about the population proportion P. So it's going to be less power. Additional testing suggests that the new vitamin tablet is more effective than first thought. Now it's believed it will reduce the incidence to 2%. Assuming the researchers use a sample of 200 children and alpha is 5%, how will the power compared to the vitamin reducing incident compared to the vitamin tablet reducing incidence to 4%? So if it goes all the way down to 2, that's more extreme, right? That means the null and the sample are further apart. That's going to increase the power. It's easier to detect a larger difference between the null and the sample that you take, which is the alternative parameter value. So it's easier to detect that when it's a larger value, so it should increase the power. That's your lesson for today.